Today we'll be talking about Euler's method, or Euler's method if you prefer. Um, Euler's method is a method of approximating the solution of an initial value problem. It will only work if it's in this form right here. Dy dx equals f of x and y. And if you have the initial condition y of x sub 0 equals y sub 0. So basically, what you need to use Euler's method is a differential equation and an initial condition. After that, something that you need to determine is the h value. This will tell us the number of partitions that are being done. We'll just set up a quick example here. So, let's say that we are using the interval 0, 1. Sorry about the bad handwriting. And we want our h value to be 0.2. So this means that we're going to start at 0, then we're going to do our step size, which is 0.2, and then we're just going to keep adding that until all the way until we get to 1, which is the end interval. The smaller the value of h, the more accurate the result will be. This is sort of like area under a curve. Like, we'll just draw a quick sketch here. We're trying to find the closer the lines are together for the rectangles, the more accurate the area is going to be. It's the same idea here. The closer together the values of this are, the more accurate your result's going to be. After we have all of this, the Euler's method can be used. Now, we'll just show you the general formula for Euler's method. It is y of n plus 1 equals y sub n plus h, which is your step size, times the function when you put in x sub n and y sub n. Now, when you are using Euler's method, it's best to set up a chart just to keep track of everything. Show you. Let's do that. I'll just show this. And it's best to put your initial condition right here. Let's just say it's 0, 1. And then you just put y n sub 1 right here. You don't really need to for this part, but you can. And then y sub n, which is the 1 value right here, or whichever value is ahead of it. And then your h, you have that right there. It always stays the same. And then the result when you put in the points of x sub n and y sub n into your function. And then to get that, your x value is going to be your step size, and your y value is going to be whatever this adds up to. So we'll just show an example of that. So we'll just start off by writing the formula. X sub n, and so let's see, our equation is going to be dy dx equals x plus y. And the initial condition is going to be 0, 1, and our h value is going to be 0.5, just for simplicity to make it easy and quick. So let's start off with y sub n, which is 1, which you can tell from the previous point, plus h, which is 0.5, times the function when you put in 0, 1 into x plus y, which will give us 1. So then here you'll put in 0.5, how much you've stepped, and the result of this right here, which adds up to 1.5. Now for the next step, you'll do the same thing, except use 0.5 and 1.5 instead of 0, 1. So we'll do 1.5 plus, and then 0.5 plus 1.5 is 2, so we'll do that. And then when you add that together, you get 2.5. So we get 2.5. And as you can see, we're at our n interval here, so our answer is going to be 2.5. Again, this is just an approximation, and the smaller the value of h that you have, the more accurate it's going to be. I did set on a calculator to find the exact answer, and I got 3.437. So as you can see, there's a bit of a discrepancy here, which is due to the step size. So now that we've talked about the basics of what Euler's method is, we'll talk about what actually it is used for, something that obviously is quite important. And for this, we've switched to the white background. So Euler's method can be used when you are given a function that you just can't integrate, and as long as you have a single point on that derivative, you will be able to use Euler's method to give an approximation of another point. So, oh, sorry, we're in white. Switch to black. So, let's say you are given a curve right here, and you know this point right here to be, say, 1, 0. Then what we do is we look at the tangent line from here, which you can calculate using the derivative, and then we can use that to approximate the point that we want to know, which say is right here. So our approximation would be right here, and as you can see, there is some little error in between the two. So this error will be if your step size is your entire interval. For example, if this is 2 right here, your h should be 1, and you go right from 1 to 2. However, if it's not that, what happens once you reach your step size right here, from here to here, is that you draw a new tangent line. So you start from your tangent line at a to 0, continues right here. But once you reach your step size, you draw a new tangent line that goes here. And once you reach that, you draw a new tangent line that goes here, and so on and so on. As you can see, the more tangent lines there are, the closer to the graph it will be. So now I'll tell you where the actual equation comes from, and for that, again, we're back to the black background. So here we have the solution graph right here, and the tangent line at the point that is given. So right here, here's t sub 0, y sub 0, t1, y of t1, and t1, y of 1. So after modifying the point-slope form, we get y1 equals y sub 0 plus the function of t0 y0, which is the slope, and t1 minus t sub 0. So now at the point that we're trying to find, we'll use the we'll make our second tangent line, which will have which will go through t1 y1, and we'll have the slope f of t1 y1. This will come out in the equation to be y equals y1 plus f of t sub 1 y sub 1 and t2 minus t1, and where t2 is a point over here. So you could keep doing it out, but it all comes to the same pattern, which ends up being yn plus 1 equals y sub n plus f of, let's call it n, times t n plus 1 minus t sub n. Now, as you can see, this is not exactly Euler's method. However, if we look back over here, we can see the difference between t sub n plus 1 and t sub n is really just the step size, as it's how often the new tangent lines are drawn. So it really comes down to be Euler's method, which, as you know, is this. So by now, hopefully you're pretty confident on using Euler's method, so we can try out a real example and actually use more than two intervals. So I drew up dy dx equals the square root of y. This we can actually differentiate, but we will just use it using Euler's method just for practice. Our initial condition is y of 0 equals 1. Our step size is going to be 0.5, but our interval is going from 0 to 4. So to start out, we'll put in y sub n, which is 1, plus 0.5 times the square root of y, which is 1. So then step size, and then what this comes out to be, which is 1.5. Now there's a bunch more, and in the interest of time, we'll just I'll just fast forward through the rest. So, after doing it all out, we get about 8.23 for our approximation. Now, as I said before, the differential equation is actually solvable by hand, but you could just use a calculator or Mathematica, either one. That will give you an answer of 9 at 4. So, as you can see, it's off by about 0.8, 0.77. So something that we'll do for this one that we didn't do before is percent error. To calculate percent error, all you have to do is 1 minus the answer that we got, 8.23, over the actual answer. And this will come out to be about 8.573 Jake.mp4. I think I just did that in my head, so not sure. I think it's right though. So yeah.